So let me reintroduce today's presentation and speaker. The speaker will be Mark Buemiller, Vice President of Particle Products for HORIBA Scientific. The presentation he'll be giving today is Setting Attainable and Practical Particle Size Specifications.
Are you turning that over to me then?
I am. You didn't catch my wink across the Atlantic Ocean?
This means I'm supposed to be serious now. I'm not always good at that, but I will endeavor. So we're going to talk about setting particle size specifications today. This is probably a 35-minute talk, something along those lines. I'll give you a little background on what should be the driving force of your specifications, which shouldn't have anything to do with the instrument, but to do with the performance of your product. We'll talk about some of the techniques we might use for the measurements, and then some guidelines specific to each technique. So why are we setting these specs? Well, very often if you're making a product, there's some kind of a specification there, which is the release specification, which has to do with the quality or the grade of the product. You might make one product, but have 10 different grades, and maybe particle size is one of the defining factors in the grades that you sell. There are also internal requirements. It could be that internally you're passing material, you're processing it and turning it over to another group within the company, and you meet the internal requirements. Or the more regulated industries actually have to worry about what the FDA or other regulatory agencies might say about what has to be done with their specifications and testing in order to have their products on the market. And since the regulated industries have to adhere to the tightest specifications, I'll show quite a few examples coming from the pharmaceutical industry, but other ones as well. And everything that I think I'll cover today would be applicable to the other industries also. So setting specifications is nothing new, and the best example I found, and I need to figure out how to get rid of the drawing tool thing. There we go. So what I found for a powder specification was something from gunsmithing in the Old West, where they talked about the black powder, the gunpowder used for guns and cannons and firearms and pistols, and actually they had the large grade, which was C, used for cannons and large devices. And then they said, then there's letter F for the finer grain, and the more Fs there were for the powder, the finer the grain. So if we go back to the Old West, then you'd see maybe a specification in the local store of FFFG for the powder for a flintlock. So how to define the size of particles is very important, and if you're loading your own bullets, I'm sure the specification is critical for both staying alive and for whatever you're going to use the bullet for. Here's just some information on sieves, because sieves have been around forever, and there are a lot of specifications I still see on the internet for all kinds of products for sieves, where they might talk about the percent retained on given sizes. Over on this side you see how mesh number is associated with microns in size. So you might see a specification for powder where a certain percent is retained on a given size. Or there are shorthand forms where people use the plus, indicating the amount retained on a sieve, and minus the amount that passes through. And they might just say, minus 40 plus 40, and this might indicate that 90% of the material passes through and is retained on these two size sieves. So this is kind of a shorthand we might see for powders if they're measured by sieves, and the specification is on using sieves to define the size and distribution. I also just kind of went around on the internet and found a few example particle size specifications, and these were for titanium dioxide. And here you see the residue on 45 microns, which is obviously a mesh size. And kind of one of the thoughts I had is for this material, it passes at 0.05% is a residue on the screen. And I was wondering, does that mean if it's 0.06% you fail? Because those numbers are the same. So really, as you look at specifications, there really must be or should be internally some kind of also a bracket of the error of the measurement, because the difference between 0.05 and 0.0502 really is insignificant. So we need to consider significant figures in everything in science. Here's another specification I found for titanium dioxide where they just said the crystal size is 0.25 microns. And that's pretty basic, but is that measured on a microscope? Was it light scattering? Is it a volume distribution? Did you hit it with ultrasound for 5 hours before you measured it? So when I look at these numbers, I have to admit it gives me a feel for the product, but it's pretty far from being an understanding of the product. And I think a more thorough specification is required to truly understand the state of the particles. So what is a definition of a specification? It's some list of tests and some kind of acceptance criteria. They're usually numerical limits. And it's usually chosen in the pharmaceutical industry to help us conform to some quality associated with the material. And we need to understand how that quality is important to the safety and efficacy of the drug in order to understand how should we be setting these specifications. So if we're working inside the regulated pharmaceutical industry, there the FDA act pretty much as the police. And if you say, well, what does the FDA say about particle size? You can dig around, and then it's buried inside certain documents where they talk about acceptance criteria for new drug products. Usually the specifications are defined when people propose to the FDA that a drug be accepted. And typically look at this particular document under question 6A, where we talk about we need to set some particle size specifications depending on how particle size affects the performance of the drug material. And there's actually in this same document a decision tree here, which is too small to read, so I summarize it on the left. And so what we're saying is if this is a solid oral dosage form or a suspension, so a solid oral dosage form means a pill or tablet. A suspension might be something that you keep in your refrigerator where it's solid particles in liquid and you take with a spoon. And what we need to ask is, does particle size affect any of these properties? Dissolution, solubility, bioavailability, how does it process, the stability of the sample, the content uniformity, does the patient get the dose every time, or even appearance. And if particle size affects any of these properties of the product, then we do need to set a particle size specification. And there isn't too much guidance in terms of what the specification should look like, but at least here we're being told, yes, these are the reasons why we need to set specifications, and at least some criteria for deciding is it important for a given material. A newer document I found on the FDA website last night was actually, so now there's quite a bit of interest in using nanoparticles for drug delivery. And if nanoparticles are being used, there's actually now a new decision tree, which is also summarized in the form on the right that you see here. And if we're dealing with nanoparticles, then the question is, first of all, are nanoparticles part of the drug product and the application? And you'll see down here, if so, what's the functionality? Is it an active ingredient or is it an inert excipient? And what is the particle size range? How is it reported? And what are the methods used to characterize it? So certainly there's an understanding that if we're dealing with nanoparticles, people want to understand what's the size range, and I'd like to see and how is that measured. The two go hand in hand. Now, if you think about, does particle size affect how the material is processed, that's true in all kinds of industries. So if you think about any particle process, it could be powder or it could be a suspension. You know, very often we're looking at size reduction steps such as milling. And there are lots of specifications which are just associated with, we wanted to go through a size reduction step such as a mill. And did we meet the specification? But there are other processing operations that can occur in the manufacturing plant where particle size is important, such as mixing and blending, because, for instance, in general, if we have narrow particle size distributions and they're similar to each other, the materials that we're mixing, it'll be easier to get them to mix to the point where it's a well-mixed material. But we can think of other processes, separation, filtration, granulation, homogenization, or crystallization, where particle size is very important. So there may also be specifications not only on the end product, but internally as the material goes through various processes as it heads towards being the final product. Not only in the pharmaceutical industry, but in many powders, for instance, if it's going to be added to a liquid and then it's going to dissolve, particle size can be very important. That might be why we're setting a specification, because particle size has a direct relationship to dissolution rate. This is one of the forms of the Noyes-Whitney equation we could use, where we could model the dissolution of material. And in here you'll see R0, which is actually the initial particle radius of the material. And this is just dx dt as it goes from a solid to a solution. Let's model how that occurs. And there are various ways that we can actually feed in information about the material and look at expected theoretical dissolution rates as a function of time. And it might be a good idea to be able to model this rather than have to go through the procedure of creating material at different particle size ranges and specifications and then doing the dissolution testing. So there are ways to look at this through modeling as well as experimental, and certainly that you can find in the literature examples of modeling compared to experimental data. Specific to something like pharmaceutical dosage forms, another important reason why we need to set specifications is content uniformity. So let's say we're feeding in a powder here, and it's a mixed powder into some kind of tablet press. And if these are particles going into each of these tablets, what we might see is here, this one particle is larger than we had wanted. And if that is an active ingredient particle, then all of a sudden there would be too high of a dose in this tablet. So the point here is we need to control the particle size distribution, otherwise we'll end up not having a uniform dose in each of the pills or tablets. And that can cause a big problem, and actually I could show you several references where materials are pulled off of the market just because particle size distribution got out of control, and this leads to concerns with content uniformity. So there is a lot of concern, especially with larger particles, in terms of setting specifications to assure uniform dose in the material being delivered to the patient. That was kind of a qualitative view. There's actually also quantitative and modeling approaches that can be used where if you feed in different particle size distributions, you can then look at the percent of, if you make 200 tablets, you know, how many of them will have exactly 100% of your dose or not quite enough or overdosed. And you can feed in different particle size distributions and then also predict what's going to happen to content uniformity. These particular examples I show here come from a publication by Zhang and Johnson. And actually, Kevin Johnson runs a small company called IntelliPharm, where their business is selling software that does this modeling. As you feed in different particle size distributions, it will model the expected content uniformity. So if we're making tablets, we have an interest in the active ingredients because of the concern with content uniformity, tablet hardness, but also size and shape because we're taking these powder particles and then compacting it into a tablet. And you can imagine particle size and shape would affect that compression. The sports analogy would be baseballs compact very different than hockey pucks. So it might not only be a particle size specification, we might also look at what's happening with the shape. When we think of suspension powders, then we do have the interest in dissolution, absorption, content uniformity, but also the ability to stay in suspension. So we might take this bottle, which might be sitting in the refrigerator, shake it, and then give it to our child if they're not feeling well. And we want to make sure that just the agitation by hand is enough mechanical force to create a uniform dose that we're giving to the child. And that will only be true if the particles will resuspend, and that could be associated with the size distribution of the active ingredient. If you're not aware of it, when you take a pill or tablet, only a portion of that is active ingredient. The rest is inert, or we would use the phrase excipients. And there are particle size specifications for the excipients that the pharmaceutical companies buy from their suppliers, for instance, lactose, a form of sugar. This is just a specification I saw for one grade of lactose. And you can just look at the particle size specification here and say, oh, obviously they're doing the measurement by sieves, and they're specifying the size distribution by the percent passing or retained on different sieves. So specifications are an important part of vendors selling to suppliers, selling to people who use it, and then this then could become an internal specification for creating the product. So that's just a few examples of where particle size would be important. Now let's talk about a few techniques and some ideas about maybe how should we set specifications for different techniques. So let's start by thinking if we're using dynamic light scattering to measure very small particles. Dynamic light scattering is a technique we might use for measuring particles that are down, let's say, a nanometer, between 1 nanometer and a micron. This technique is based on the particles moving due to Brownian motion. We inspect a sample zone with a light source, and with this detector we start looking at the change in either a photon count rate or a shift in the frequency due to the motion of the particles. And from that, we're going to create the particle size distribution. So depending on the technique, maybe we're looking at this frequency shift from the motion of the particles. But there are kind of two ways we can do measurements down in the size range using dynamic light scattering. Either way, we're going to use a light source and a detector, and we're going to look at the light scattering from the Brownian motion of these particles. Then we can either look at a power spectrum from a frequency shift, or just feed photon count rates into a correlator. With either approach, we then come up with, here D is actually the translational diffusion coefficient, and calculate the radius of the particle using the Stokes-Einstein equation. So for small particles, 1 nanometer to 1 micron, we are probably using dynamic light scattering for these measurements. And let's talk about now what values from dynamic light scattering might be important for use in setting specifications. Well, often when I start providing some advice, I try it to not only be advice from yours truly, although he's experienced, perhaps I'm biased or occasionally even wrong. So I'll usually tell you when something is just in my own humble opinion. On a slide like this, what I'm going to show you, though, is what is suggested through the agreed-upon ISO standard. And for particle size analysis by dynamic light scattering, the ISO standard is 22412. And this is just kind of an updated version of the previous one, which was just for instruments using correlators. This was written for instruments using correlators or power spectrums. In either case, if we're going to use DLS, some of the suggestions from the standard are take measurements at least 3 times. And that's something I usually recommend in particle size. Only believe something if it is repeatable and or reproducible. It's all too easy if we do a measurement and we like the looks of that number to just say, I'll go with that. But if it's not repeatable, we're not quite sure if that's really the value that we should have faith in. So when using DLS, let's take multiple measurements. What we're going to then do is maybe take the average of those 3 measurements and what numbers are we going to use for our specifications. And in the ISO standard, what is suggested is the Z average, which is the average particle size from the intensity distribution. In the ISO document, it actually uses the connotation X bar DLS to talk about Z average. So that is basically the central point of the distribution. And then how do we describe the width of the distribution? How broad is the distribution? And that is actually the polydispersity index. So if we're using dynamic light scattering, the 2 values we're probably going to use for our specifications will be the Z average and the polydispersity index. We have run 3 measurements, hopefully, and what we're going to do is make sure it's repeatable within 5%. If it isn't, we need to find out what's going on with the experiment. If I see a greater than 5% variation over those 3 measurements, I take the cell out and I look at the bottom of the cell. Are there particles visibly present? Did they settle during the measurement, which would indicate there are particles that are too large to really measure using dynamic light scattering? So just a visual check gives you some information. What is also recommended for many samples, if you're willing to put in the time, is a dilution study. And especially if it's the first time you've measured a sample, I think that's a good idea using DLS. Although all of the vendors of DLS instruments now say, yeah, we can work at high concentrations, you're still not really sure if the value reported at the high concentration is truly the most accurate. So when we're doing work developing the specification, it makes a lot of sense to do a dilution study. And we have a separate webinar on our website talking about using dynamic light scattering and how to interpret those results. And in general, we're just going to say here, dilution studies are a good idea, and if we see it changing with concentration, we need to know how to interpret that data. The ISO document just says use the value from the most dilute result. The answer is a little more complicated. I think we'll just refer you to another webinar on our website to go through some details there. Like every other technique, you should verify the system on a regular basis. In the ISO document, they suggest using a 2%, they suggest using a 100 nanometer polystyrene latex sample, and they say it should be within 2% of the reported value. Then also let's do multiple measurements. They say let's test repeatability, and they say the polydispersity index should be below 0.2. Now, I sit on these committees, and I sometimes wonder, after these get out into the field and I start looking at the standard versus reality, and to be honest, compared to the real world, I think these specifications in the ISO standard are a bit tight. And when you're in these committees, there's always pressure to both say, let's drive people towards best practice, and there are always whatever other dynamics are going on in the room. So actually, I look at these specifications, and now we're in the world of my own humble opinion. I think these numbers are a little tight for reality. And as far as I'm concerned, if you're using DLS, and you're using, it's a typical day, and I'm using a PSL, if you're within 5%, I think that your instrument is probably just fine, and you're probably just dealing with sample preparation, salt concentration, things like that. And on a day-to-day test, and even something more rigorous, I would say that the values in the ISO document probably a bit tight. So if I'm using dynamic light scattering, if we're going to be setting specifications, you know, the only agreed upon values out of DLS are the Z average and the polydispersity index. But in the software, there is the ability to convert the intensity distribution to a volume distribution. We just need to know the refractive index of the sample in order to make that conversion. And that conversion is something some people use in their specifications. It can dramatically alter how the results look. They're the same results. And typically the people who I see doing this conversion to a volume distribution are people in industrial settings, making industrial products. And there I do see people do conversions and then setting specs on D10, D50, D90. And you know, if that's your history, then there's probably, hopefully, a good reason why you've done that. And I do see specifications written that way. But within the agreed upon ISO realm, there's really just the average and polydispersity index. Another very popular technique for particle size is laser diffraction. I'm not going to go through how it works. All I'm going to say is, based on light scattering, the sample goes through a cell. These are just pretty pictures. You know, we look at the diffraction, but really it's just a light scattering instrument. This is the LA950, our laser diffraction instrument, which has a very broad dynamic range, as you see stated here. But all I'm going to say now is, if you're using laser diffraction, let's discuss how we might use the results in order to set specifications. If you want more details on how this technique works, go to the website. We have separate webinars on the theory, on refractive index. I think Ian just gave a very good webinar a week ago on how to interpret these results in detail. But what we're going to talk about today are, what are the most important values first that come out of this result? And typically people first look at a central value of some type. And here are two particle size distributions. The blue is a little more narrow, then the green one's a little more broad. And what you'll see is, since these are symmetric distributions, the mean, median, and mode are all the same for symmetric distributions. So the mode is the peak of the frequency distribution. The median, denoted here, this is the diameter at which half the particles are larger than and half are smaller than this diameter. And the mean is some kind of calculated value, like an average. And so for symmetric distribution, these are the same. And in general, we don't suggest keeping a specification on just the central point of the distribution. Consider what we see here. These are obviously two different particle size distributions, the blue and the green, but they would have the same central value. And you could say, well, the average particle size, or the mode or the mean, is 100 microns, but if we create this product, it's very different than that product. So in general, we recommend also including some information to describe the breadth of the distribution. And the values that we frequently use to describe the breadth of the distribution are the numbers D10, D50, D90. The D50 is that median value where 50% are above and 50% are below this diameter. The D90 here, 90% of the particles are below this diameter. And here's the D10, 10% of the particles are below the D10. So these are the numbers we will typically use when I talk about setting specifications using laser diffraction, the D10, D50, and D90. Now 100% of the particles would be below the D100. And this is a number of interest in specifications, and I understand why people want and occasionally need to include some specification like that. But we do need to warn you, in general, that D100 is not a robust calculation when using laser diffraction. A single bubble, a single thermal fluctuation could create a change in your D100, which actually is not significant in terms of any real change in the size distribution of your product. So in general, here's one of the first hints I'm going to give is don't use that D100 from laser diffraction. I understand the temptation to, but we do not recommend doing that. So let's go back to our two distributions, the blue and the green. So they might have the same D50, but if we use three numbers to describe or specify this material, the D10, D50, and D90, then we can actually pick up on the difference between the green, more broad distribution and the more narrow blue one. So if we specify these three numbers, then we can actually understand the difference between these two different products or two different creations of a particle size distribution. So here now we have an asymmetric distribution. There are a few larger particles and smaller ones. And what we see here is when it's a skew distribution, the mean no longer equals the mode or the mean. And if it's skewed to the right side, then actually the median is a little larger than the mode and the mean is a little larger than that. So here we're going to talk about for the first time the mean, which is the D43. This is the volume mean, which is the typical mean calculation used when using laser diffraction. And this is actually going to be the number we might include inside the specifications. Here is a description mathematically of the D43. It's just defined here, and you can find the description in several ISO or ASTM documents. When you're using laser diffraction, and if you're using, in particular, HORIBA software, if you just see mean distribution when you're looking at the volume distribution, that implies the volume mean or the D43. So I mentioned the D43 is sensitive to the presence of large particles. I just wanted to show you an example of this so you could understand if it's a value you should consider in your specifications. So here are two measurements made from our applications lab. They're very similar distributions, but the blue result has a small amount over here of large particles. So what we're going to see here is the D10, D50, D90, and what you'll notice for the two different results, these numbers are essentially the same, 0.2, 0.4, 2.7. So even if you go out to the second decimal point, these numbers look extremely similar. But what about these few large particles? If we set the spec on D10, D50, and D90, we probably wouldn't catch the difference. We wouldn't catch these few large particles. But if we included a specification on the mean, the D43, we'd actually see that goes from about 1.1 to about 1.3. So here we see there's a 15% difference in the reported mean value, and that might be a large enough difference where we could now catch that and understand there's a change in the product, and we catch that through the use of the D43, the volume mean. And it might be important, for instance, the classic application I can think of is CMP slurries in the semiconductor industry, where we're interested in catching those few large particles, and if that is the goal, then the D43 is perhaps a number we should consider including in our specification. I want to now show an example of an unusual case that we need to think about. What if we have a bimodal distribution, similar to what we see here? So if we know that every time we create the material, it's a bimodal distribution, which of these numbers should we use? Well, the D50 is still an option, even if the D50 sits around here and there aren't many particles there. The D50, in my humble opinion, is still a number to consider because it is still the most robust calculation created by a laser diffraction experiment. So we could still keep our specification based on the D50, but if it's more important to understand the two peaks of these distributions, then we might have to consider additional numbers. Maybe it's the modes of the two distributions. Maybe it's the percentage in each peak here. And what can we do in this situation? Well, actually, in our software for our LA950 diffraction analyzer, we actually have a fairly sophisticated bimodal distribution result algorithm where we can show the statistics for the overall distribution or for three separate peaks. Here we see on the far left-hand side the D10, D50, D90, and other statistical results for the overall distribution. But then we see the first peak has a mode at 1.4 microns, and the second peak has a mode at 47 microns. we can find out the percent in each of these. And actually, we can split that distribution and start getting the distributions on each of these two separate distributions. So if we do have a bimodal distribution, life can get more complicated, but certainly the software is now sophisticated enough we can provide close to full statistics for each of those two distributions. Once again, we should also look at what standards exist in order to understand how to properly set specifications. In the laser diffraction world, we have ISO 13320, which is applicable to all industries. And in the pharmaceutical industry, if you're on my side of the pond, we use EP 2.9.31, and if you're on Ian's side of the pond, you use USP 429. They're essentially the same standard, the same document. They're both based on ISO 13320. And some of the important comments that come out of these standards is, first of all, we again need to test reproducibility. Don't believe anything unless it's reproducible. And also, if we're using this for release test, for specifications, let's make sure we verify our system on a regular basis. I have a separate webinar on the website on verification of systems. I'm not going to go into that today, but I am going to point out it is an integral part of both standards. So if we're going to follow these guidelines, we're going to prepare our sample, measure it, drain it, and repeat that 3 times. This is not just recirculating the sample 3 times. This is 3 independent preparations of the material. We're going to record the D10, D50, D90. These are the numbers we will typically use for our specifications when using laser diffraction. We're going to look at the average values from those 3 measurements. And then we're going to calculate the coefficient of variation, the standard deviation divided by the mean times 100. And what we're going to do is make sure, if we're following the ISO guidelines, that our coefficient of variation is less than 3% at the D50 and less than 5% at the D10 and D90. In the pharmaceutical world, if we're following these guidelines, and actually those numbers expand up to 10 and 15%. So broader goalposts allowed in the pharmaceutical industry. I don't think I'm going to comment on why that's true because I wasn't part of the committee that created this. I can come up with some theories, but we do have broader goalposts in the pharmaceutical industry. And also, if the D50 is under 10 microns, we're allowed to double any of these numbers, and I think this is just associated with the fact that as particles become smaller, it may become more difficult to disperse the sample. And then if sampling becomes more of an issue, then we should expect there to be a somewhat broader coefficient of variation when doing multiple measurements. So, should this reproducibility be part of my specification? And in my humble opinion, you're probably not going to share with all of your customers that you do this, but I would recommend it as part of your internal specification. If this is a serious product release test, and if the numbers really matter to the performance of the product or the happiness of your customers or the safety of the consumer, I think it is critical to actually do the reproducibility testing. But your release specification might just be on D10, D50, D90. This is, maybe you'll just say it's part of your method, but I think it should be an integral part of how you collect data prior to releasing the product. Now, there are a lot of calculations there doing coefficients of variation on various results. We've automated all of this in the LA950 software. So you see down here you can live with, I'm going to work within the USP environment, the ISO environment, or create your own pass-fail specification. Run multiple samples, and these calculations are automated for you, and you can just get a quick printout of pass-fail. If we're using this system for product release tests and the data is critical, verify that system on a regular basis. All I'm going to say today is in the standards, we don't use polystyrene latex so much anymore as we use polydispersed materials. So rather than monodisperse latex, the standards suggest using polydisperse. Do multiple measurements, have a pass-fail criteria on both the accuracy and the repeatability, showing you the pass-fail criteria here. And I apologize if I switch from showing D50 to X50. The reason I do that here is actually in the standards they use X values as opposed to D, and really this just turns into a almost a language, what country do you come from point. The original ISO document was driven by people who came from Germany, and Germans happen to like X's better than D's. In the newest version, there's actually a statement in there, we're talking about the same thing. So anyway, so we should have an accuracy and a repeatability pass-fail criteria when measuring standards, and then we know the system can be trusted for the measurements for the release of the final product. The verification is very important. We've actually automated this in the LA950 software as well. You can say I'm doing a USP or an ISO verification. They're basically the same. Do the 3 measurements and automatically get the pass-fail criteria. Keep that associated with the instrument in case you're ever inspected, or just to live within your own ISO guidelines of the quality of your system. So now let's get back to the actual specifications. Now, if we're in a regulated industry, what kind of things should be included in that specification? Certainly the procedure we used, the sampling, the dispersion, did I use ultrasound? Did I use a surfactant? In these industries, they actually have to worry about method validation. Separate discussion on that probably on our website, or perhaps Ian, one that you and I should do someday. There should be an acceptance criteria of both upper and lower limits, and in there, representative plots of what did the results look like. For every step along the way where we had to make decisions, there should be justification to back up these decisions. And the justification usually looks a lot stronger when you're making reference to the standards of pharmacopoeia in terms of saying these are the reasons why we made these decisions when creating the method and setting the specifications. And there really should be some kind of a range expected from both the instrument and the manufacturing when setting these specifications. So let's look at a few example specifications. Perhaps we measured a sample using laser diffraction, and we have a spec on the D10, D50, D90, and maybe the D50 should be around 25 microns. Now there are various ways we could set that specification. We could see here, well, the D50 should be 25 microns plus or minus 15%, just showing the range here in particle size. The D10 could be 8 plus or minus 25%, and the D90 75 with a range of plus or minus 25% here. So I look at, and maybe the D43 if we want to be very sensitive to the presence of large particles. So I look at the specification, and then as I looked at it the other day, I said, well, that looks like a pretty busy specification. And what I will sometimes see, and this is often sufficient, maybe not always, is people just reporting saying the D50 can be not more than 25, the D10's not more than 8, and D90 not more than 75 microns. So here is perhaps a cleaner way to show the specification, but certainly this is a bit more rigorous and probably reflects a higher interest in the quality and control of the product. Which way do you go? It really should be driven by how important is particle size to the performance of your product. But any of these specifications look better than something like we saw at the beginning, crystal size equals 0.25. So both of these look better than that, but 2 different routes to go to actually look at setting and perhaps communicating the specification. Here's an example specification I found that had been approved on the FDA website, and that's what you see here, the D10, D50, D90, and the specification calls out for not more than given particle size ranges. So I have seen examples where this has been accepted by the FDA, but before we end in a few more slides, I might show you an indication that they would like to see a little more than that. If you'd like to see what has been published in the literature on setting specifications, I'll point out this article published in American Pharmaceutical Review a year ago. And this actually reminded me, this is showing 6 different batches of this active ingredient, specifications on the D10, D50, D90. And when you look at the relative standard deviation, that looks a bit large, but then I was reminded as I read the text, this not only has to do with instrumental differences or errors from the laboratory, but also the variability in the manufacturing. And if these are multiple batches of the material over 3 different years, this could actually be a larger source of the variation than what goes on in the laboratory. And would this be acceptable? That's not really for me to comment on, because I don't have the feel for the sensitivity of particle size to product performance here. But here is one reference I can give you to setting specifications in the pharmaceutical industry. Another one I can give you, I just found on the AAPS Pharmaceutica website. This was a presentation given by Zhi Gong Sun at an Arden conference last year. I was going to go to it. February 4th happens to be someone's birthday. He wanted to be home that day. But I'll show you a few slides from this talk. I know Zhi Gong. He used to work for me at a company I used to work at. And he and I have shared a few slides and been involved with a few conferences through the years. And Zhi Gong, who now works for the FDA, but of course every time he talks in public, he has to tell you what I'm saying today doesn't necessarily reflect what the FDA is going to enforce in your lab. But some slides from his presentation actually looks at D10, D50, D90, and kind of talks about what is the acceptable range for these values. And that as you do your testing, you should understand what's the range of errors that comes from your analytical techniques. And then as you look at how am I going to set specification, if you just say the specification is not more than certain sizes at D10, D50, D90, he kind of throws out there that might not be completely adequate without scientific justification. So here is someone saying, you know, I see this going on, but you know, you'd better tell us why you don't really need to talk about a range of values when you set your specifications. We also see here, you know, when you look at a particle size distribution plot, particle size is on the x-axis, percentage on the y, and on this slide we're going to talk about where should I set my specifications, on the x or y-axis. So do I set my spec at the D10, D50, D90, which is sized on the x-axis, or percentages, which show up on the y-axis? So if I say 50% of my sample should be below 100 microns, that is not quite the same as saying the D50 is 100 microns. If the D50 is 100 microns, and if there's sampling and instrument and error in the lab of plus or minus 5%, then my D50 is going to vary here by 5%. But now if I project this out to the percentage on the y-axis, that ends up being an error of 20%. And so in general, we recommend setting specifications on size and not on percentage. Yes, they are the same thing in terms of what we're going to specify, but everything looks better when the error bars are smaller. So in general, we recommend using specifications based on size, not on percentages, as you see here. So we're getting down to the last few points on setting specifications, and we've decided now, all right, because of the performance of this product, we want the D50 to be between 80 and 120 microns. But we also know there's some error in the measurement or in the sampling, so we actually have some kind of error from the laboratory. And what we need to do is then include this understanding and internally set our specification tighter than the external specification, so that if I do my measurement here and I know there's an error, there's no chance it actually is outside the specification range here. Or if I measure at this end of the distribution, there's no way it's smaller than here. So the more narrow our error in the laboratory, the easier it really is to hit the specification, which is the external specification based on product performance. I give you the reference here where you could see the justification, but hopefully it's now intuitively obvious. And what this drives us to is it makes a lot of sense to be very careful in the laboratory, because that will make it easier for you to ship product out the door. So the point here is we have to tighten that specification knowing what the laboratory error is. Therefore, let's minimize that error. And how are we going to minimize that error? Basically by getting the measurement done right. By getting the sampling right, using a structured approach to method development with an eye on the goal of reproducibility. And we do have multiple webinars on the website addressing the issues of sampling, dispersion, structured method development, of using our new wizard inside the LA950 software, the Method Expert Wizard, to make sure we have a structured approach to minimize this error when we create good methods. So let's wrap up with a few conclusions. You know, these specifications should all be based on product performance, not on what goes on in the laboratory. The only way the laboratory kind of mixes into it all is we have to understand what technique was used, what data, what points on the distribution should we use for setting the specification, and then do we need to tighten the internal specification in order to make sure that we never ship out product outside of the range of the expected performance specification. The two techniques I focused on were dynamic light scattering, where the Z-average and polydispersity index are probably the approach we're going to use for setting specifications. And with laser diffraction, we're probably using the D10, D50, D90 from the volume distribution. Look at the standards. They provide some good guidance of what is suggested good practice, and also to benchmark yourself against other labs to understand how should we test our reproducibility. And then just a few other hints just before I wrap up. Avoid using the D100 with laser diffraction, and only use the mean value, the D43, if you want to be more sensitive to the presence of large particles. So I think I just show here how you can get some more information from us, and also on the last slide. This is one of the URLs that will get you to the particle characterization page within the HORIBA.com website. In here you will find you might need to sign up to get into the download center to watch the previously recorded webinars on things like diffraction theory or data interpretation. And there's also a little sign up here for the newsletter if you'd like us to be in touch with you. Just something we send out once a month. We try to update the website with new application information, etc. every month. That's how you can make sure we can stay in touch with you. And I was trying to finish at 5 p.m. local time. I was within close enough time here. I thank you, everyone, for your time. And Ian will slow down now and ask you, how are we doing? Did we raise any questions along the way?
No questions yet, so now would be a good time to start sending in those questions. We did get an admonishment that apparently there were some bad words heard in the background. So,
you know, I heard that too, and it sounded like crosstalk from somewhere, because from where I'm sitting, it didn't come from my environment.
yeah,
Did you hear it?
I didn't, but I was muted, so we'll just chalk it up to the intertubes.
All right. Apologies to everyone. I kind of heard a little bit of that too, and I figured I was better off talking over them than trying to figure it out as we were working through that period.
Yeah, no, I apologize too. Typically, Mark and I like to be the ones who give the bad jokes and the dirty jokes, not have someone else give them during our presentation. But all apologies.
And I only swore in French today. That's okay.
Sacre bleu.
Everyone says that word here.
Well, there is a strike on, so.
Life is tough in Paris, I got to tell you.
All right, so we have our first question. Ryan asks, what was the name of the equation that had the RH particle size calculation? So I'm guessing that's hydrodynamic radius? Maybe not, though.
Yeah, probably. So when we use dynamic light scattering, that was the Stokes-Einstein equation. By looking at the Brownian motion, we actually find a route to determine the D value, which is the translational diffusion coefficient. We then use Stokes-Einstein to calculate RH. Radius is R. And the reason we have H there is because it's the hydrodynamic diameter, which is basically, you can think of it as a sphere of what diameter would diffuse using, would have this diffusion coefficient. So it is hydrodynamic, and I think that's actually a good point. When looking at DLS data, it's always the hydrodynamic diameter. And for non-spherical particles, just be forewarned, it may be different than what you'd see from a microscope or other technique.
All right, thanks, Mark. We're running a little bit light on the questions. Well, heavy on the positive comments, though. Thank you, Ryan, for the compliment. All right, here we go. A new question from Marie. I understand the volume mean diameter, but do the numbers D43 have any meaning like the D10, the D10, D50, and D90?
They do mean something, but D10, D50, D90 are specific, percentages under. So the D90, 90% of the particles are below that diameter. The reason we use D43, I might as well go back to that slide. Let's see if I can do that. Is it's just kind of showing you the exponents used in the calculation, and that's why it shows up that way. So what you do is, if you ever want to manually do this calculation, is you look in the histogram table from the result, And what you do is you actually look at, for each band in the histogram, you look at within this histogram band, kind of it's the geometric mean diameter. So you take the upper histogram band diameter times the lower, and you take the square root. That's the number you're going to use for D. N is the percent inside that diameter. You take the D value, raise it to the 4th power. And down here in the denominator, we use the 3rd power. So it's just showing the powers used in the numerator and denominator in the equation. And the old chemical engineering thing you always check with every problem, then you get the units in the fashion you want, right? 4/3 will then give you singular virgin microns. So that's why it's just referred to as D43, because of those exponents in the equation.
Okay, well, I think at this point I'd mention again that both my email address and Mark's email address are in the chat box. So if you have any other questions that you think of at any point in time, if you're a giant particle size nerd like me, you actually dream about work and about particle size questions. So even if it occurs to you in the middle of the night, go ahead and shoot that off to us. Otherwise, we have tons of information on our website. That URL is also posted into the chat box. I'll remind everyone, if you're new to HORIBA's webinars, that we record every webinar presentation so that we can post the video and the presentation slides in the download center of our website. So I would check back within a few days to make sure that that's up. I'm usually the one processing the video, and I have a bit of a deadline. I leave for Japan on Thursday, so I want to make sure I get it up before then. Otherwise, I think...
I'll be seeing you next, isn't it? The weather's going to be beautiful over there. Have you seen that? Well, you don't care. You live in California.
I do care. It's actually quite nice right now. There's a thunderstorm. Naturally, I'm missing it. I never get to see the thunderstorms, and I like them so much. But anyway, that's a little bit of complaining from someone who's not a native Californian, I suppose. But I think at this point we'll wrap up the webinar.
You forgot your joke.
Oh, that's right. I apologize to those of you who waited through Mark's terrible presentation for my amazing joke. I'm also sorry that this is going to be completely disappointing.
I pity the fool that does that.
Oh, my goodness. We have to end this quick, so here we go. It's a bit of a subtle one. Are you ready? Have you heard that entropy isn't what it used to be? That's it. That's
quickly dissipating here.
Yes. You really saved that. Thank you. More heckling from the peanut gallery. So this is the extra special value you get attending a HORIBA webinar presentation over anyone else's. You get all this added value. You know, two guys laughing at stupid jokes.
At themselves.
Mostly at themselves and sometimes at each other. But all right, so we'll bring the webinar to an end. You guys should do a morning drive time radio show. Well, there you go. I think it may pay better. Actually, it's radio, so probably not.
We both have tough commutes. You know, you think you have a tough commute. You should see traffic in Paris. Oh, my God. It's tough.
You're always trying to one-up me. I'm pretty sure Los Angeles takes the cake anywhere that's not called Kyoto, or I'm sorry, Tokyo. But anyway, enough of our inane banter. I have to go prepare to teach one of our user training courses. We have a boot camp going on in Irvine today, so I need to go start looking at those slides so I don't seem completely out of my element. Thank you, everyone, for attending today's presentation. I hope you enjoyed it. I know that we did, and I hope you have a wonderful rest of the day. Thanks. Goodbye.
Okay, bye, everybody. Thanks for attending.